Prashant sir, Ingule sir.
हाँ सर.
Meanwhile, just can you give the outline of tomorrow's schedules? That because tomorrow we are having the different time schedule. So can you meanwhile just give the brief tomorrow's schedule to the participant, those who have been joined?
Okay.
Because I think at 2 o'clock we will be starting the session, and it 2 to 3:30 the session. Welcome, sir. Welcome, Ashish sir.
Yes, good evening. How are you?
Just fine.
Welcome sir.
Nice to see you once again.
Good evening, Satish sir. Good evening. Welcome.
Good evening, sir.
Happy birthday from the Department of Communication, sir.
Thank you very much. And wish you all Sankashta Chaturthi also today. So wish you all happy Sankashta Chaturthi.
I think it's a nice day. Today is your birthday, and we are fortunate to have the speaker like you today for this FDP. So I think this is one of the date we had been. Means it has been get matched, birthday and the presentation also.
Hopefully,
today's our course also is having the birthday. I mean, there are 2 persons in the meeting who are having the birthday today.
So the party will be the talk, nothing else. Yes.
You need to have to come to Oman if you need to have to party from your side.
You are always welcome, sir. Party due for you.
Sir, we will wait for 2 minutes and then we'll start, sir.
Sure. Many people are joining now.
Many are joining.
Because, sir, Ashish sir, what is that we had kept our time 6 o'clock. So within 2 to 3 minutes, almost most of the participants get joined, and later on we will start. Formally, our session will be started.
Sure, sir. Please take your time, sir.
Prashant sir, can you make my video on?
Yes, just a minute, sir. Done, sir.
Yes, good morning. Good evening.
Good evening.
Happy birthday, sir.
Thank you very much.
Can we start, sir? Vishnu, sir?
Yes, I think we start. Because see, meanwhile, when we'll go through the formal introduction of today's speaker, our session will be started. Meanwhile, the participant will be getting joined. So, Ravi Dapre sir, will you just formally introduce our today's speaker so that we can start our today's session?
Yes, sir. Good evening to one and all present here. It gives me immense pleasure to extend a warm welcome to everyone gathered for the 5th day and the 9th session of the AICT Atal Faculty Development Program on Emerging Sustainable Practices in Chemical Engineering, organized by the Department of Chemical Engineering, Datta Mekhe College of Engineering, Airoli, Navi Mumbai. On behalf of our college management, respected principal sir, coordinator and head of the department, Dr. S.M. Deshmukh sir, co-coordinator, Dr. P.M. Ingole sir, faculty members and organizing committee members, I take this opportunity to welcome our esteemed resource person, Dr. ASHISH GUJRATHI sir. Dr. ASHISH GUJRATHI sir currently serves as an associate professor in the Department of Petroleum and Chemical Engineering at Sultan Qaboos University, Oman. He holds a PhD from BITS Pilani, where his foundational work was on Pareto optimal solutions using evolutionary multi-objective optimization, a topic that remains central to modern engineering design. Sir is a recognized scholar, receiving the prestigious SKU Distinguished Researcher Award and multiple Oman National Research Awards. Under Sir's guidance, 10 PhD students graduated and 26 postgraduate students. His research has yielded over 57 peer-reviewed publications, with a significant majority appearing in Q1 ranked journals, published one book, attended and published papers in 58 conferences, 4 book chapters. His specialty is in advanced computational methods, including the application of evolutionary algorithms and machine learning techniques to solve complex problems in sustainable energy and petroleum process optimization. His works demonstrate how to move beyond conventional stimulation to truly optimize industrial processes. He has been an honorary consultant for industrial projects and has served as a resource faculty for professional development programs for companies like Hindustan Zinc Limited. Crucially, he has organized and led multiple workshops on industrial standard simulation softwares like Promax and Aspen Plus for both students and professional engineers, showing his dedication to translating advanced tools into usable skills. His mentorship is proven. He supervised the team that were the winners of the Honeywell Unisim Design Challenge, a clear signal of his ability to foster innovation. He served as a key coordinator for the ABET accreditation process for his department, leading the faculty through the complex transition and mapping of the students' outcomes. He has actively modernized his curriculum, introducing extensive MATLAB coding and emphasizing optimization and sensitivity analysis to better prepare students for the demands of the 21st century industry. We are deeply honored to have Dr. ASHISH GUJRATHI sir with us today as a distinguished speaker for the Atal FDB program. Today, he will be enlightening us on the transformative theme of sustainable green chemical technology. We are confident we are deeply honored to have Dr. ASHISH GUJRATHI sir with us as a distinguished speaker for the Atal FDB program. Today, he will be enlightening us on the transformative theme of sustainable green chemical technology. We are confident that his innovative perspectives and practical insights will greatly enrich our understanding and ignite new ideas towards sustainable development in chemical engineering. On behalf of the organizing committee and all participants, I extend a warm and respectful welcome to you, sir. We eagerly look forward to an enlightening and inspiring session under your guidance.
Welcome, sir. You can start your presentation, sir. Ashish, sir, you can start your presentation.
Yes. Thank you, Dr. Ravi. Thank you, Dr. Ravi, for introducing myself. I'll be giving my invited talk on sustainable green technology. As you know, I mean, these words, the the sustainability, and the green, and indeed our chemical engineering domain. So when I talk about chemical engineering domain, we should talk about not only the oil and gas, which is the major, which comes under the major domain, but also the chemical engineering plants, the oil and gas plants, and indeed the petrochemical plants, polymer plants, biochemical plants. So the range is very wide. The kind of products that the chemical engineers are dealing with, the range is quite wide. Now, with such a wide range, now if you bring the sustainability and the green together, that means the title is going to be very broad. So I will try to cover this very broad title under a very one of its branches called like optimization approach, where we focus on multiple sustainable objectives. So the key idea here is that if we are able to sustainably reduce the energy demand, that will contribute directly towards meeting the sustainable green approach. Because if you are able to reduce the energy, we are going to save the fuel that is going to produce CO2. So there is a direct relation between the CO2 emissions and the energy that we are consuming. When you consider the profit will come from the product flow rate, and the product flow rate by managing the resources. So the maximum product quality and the maximum product flow rate also deals with the the sustainable approach. This is why the engineers across the world are continuously working to increase the throughput of the chemical plants. I will divide my talk into broadly into the biochemical, oil and gas, and chemical processes that we have adopted. Before we go to the optimization, before we talk about the processes, we should understand that optimization refers to finding the best feasible solution. Either you talk about maximum or the minimum, the ultimate maximum and the ultimate minimum. Both of them are called as the optimum. So this can be either single objective optimization or can be have multi-objective optimization. When we talk about multi-objective optimization, that means we are talking about two or more than two types of objective functions together. Those objective functions can be from can be there from the process point of view. They can be from process, like you want to maximum the profit production rate, you want to maximize the yield of reaction, or you want to can we mute all? Sorry. So the objectives can be either from the process point of view, like we maximize the productivity, or maximize the yield, or minimize the byproduct simultaneously. This word simultaneously is very important when we talk about multi-objective optimization. It can be process and energy together, or it can be the process and emissions together, or it can be the process and safety aspects together, or it can be in combination of all 2, 3, or 4 of them together. So number of economic, energy, process, environment, energy, and safety-based criteria are widely applied in the chemical engineering domain. So in multi-objective optimization, the decision makers are always interested in getting the Pareto optimal solution, which is also called as the set of equally good solutions. When we compare the stochastic or the evolutionary population-based search algorithm, they are far different than the classical or the deterministic algorithm. Where the classical algorithm, they start with single solution and ultimately they result in single solution. They often limit themselves towards reaching the non-optimum solution, because their background remains in starting with single point, and they follow the fixed transition rule, like Newton-Raphson method. In Newton-Raphson method, we know that the next point is always current point plus some kind of the addition, or some kind of formula that is added, like xi plus 1 is equal to xi minus fxi over f dash xi. So that fxi function value at xi over the derivative of that function value f dash xi at the current point. So this is going to be the differential which will be added. So that means from one point to another point, that another point to the next point to another next point, the transition is going to be the fix. There is no differentiation. In stochastic algorithms, we see that we go for randomness, and because of the randomness, there is a better chances that the optimum point can be easily approached. So in multi-objective optimization, we often we deal with two types of search spaces. Those search spaces are the decision search space and the objective space. So if you see the decision space, where we plot the decision variables like temperature of a reactor and the pressure of a reactor. And if you want to see the influence of temperature and the pressure, decision variable 1 and 2, when we apply these changes in those variables, in the temperature and pressure, and when we want to see the impact of this change in temperature and pressure on the objectives, like you want to maximize the productivity and you want to minimize the byproduct formation from the reactor. So in that case, we are going to get another search space. So dealing with two types of search space is the key for multi-objective optimization. The reason why they are said to be more complex. They are, whenever we deal with solving such kind of problem, they are referred to be, from the search point of view, they are referred to be more complex. And the more is the complexity, the more is the complexity of the search space, the more challenging is going to be the aspects of obtaining the results. And that the more the challenge, that the way we say, the more is the challenge, the more is going to be the realistic solutions. So we can divide the multi-objective optimization broadly into mathematics, medicine, science, and engineering. In engineering, we can divide into chemical, oil and gas sector, where we talk about the gas operations like gas sweetening, gas dehydration, isn't it? And the oil-based operation like hydrocracking, hydrotreating. Number of operations are there in the refinery. Refinery is full of problems, if you understand. If you see the refinery, I mean, right from naphtha cracking, right from hydrocracking, hydrotreating, isn't it? The fluid bed catalytic cracking, isn't it? Vis breaking. So each of the process has got is highly complex, dealing with hundreds of reactions happening simultaneously, and to model such kind of problems is not we cannot say that it's going to be a straight aspect. So often it takes efforts, and the challenges are quite wide when you talk about oil and gas based aspect. The chemical engineering problems like H2SO4, vinyl acetate, there are a number of chemical processes that we deal with, isn't it? So those are also the processes where multiple objectives like process, energy, safety based aspects can be focused. Pharmaceutical industries, which also comes under the chemical sector, and the minerals processing. Minerals processing like the iron production from the from the ores, or the aluminum production, or any kind of cobalt, or any kind of metal or non-metal production. So that will involve dealing with solids, and to model such kind of process, it will need extra knowledge of dealing with solids. Particularly, our group have successfully solved to me hundreds of problems. I can say that these topics are, though they look to be bulleted, but they belong to the PhD titles of some of the students, and often MSc work from the students, or from the industrial projects that we solve. And each of the problem has taken not less than 1 year to solve and to get published. So styrene manufacturing process, right from adiabatic and the adiabatic and the pseudo-isothermal operation, then low density polyethylene reactor, which comes under the polymer sectors, PTA oxidation process, another very complex process, polyethylene phthalate wipe film reactor, where we deal with multiple phases like polymers, then gases, and the polymers are also the dead polymer and the live polymer. Nylon 6 polymer manufacturing process, solar desalination with phase change material. So in this case, the wax is used as phase change material. So it's right from solid to the liquid phase, its heat transferability will keep on changing. So that aspect has to be considered in the desalination process. Pyrolysis of jatropha residue, de-oiled cake, supply chain planning, waste office papers for cellulose production, extractive desulfurization of liquid fuels, naphtha cracking, ethane cracking, large-scale ammonia production with water electrolysis. When we say large scale, that means we are talking about industrial scale, and the idea here is adding the title to as large scale is to relate the work to the industrial processes. Lysine fed batch fermenter in the biochemical sector, cell recycle based continuous lactic acid production, occupational health and safety for process industry, green ammonia production, large scale methanol production, water flooding in oil fields. So the water flooding in oil fields, when we say, that means we are talking about the oil and water present in the earth. So in the porous part of the rocks. So often such oil wells are spread over kilometers, and the depth also is often several kilometers. So getting the geoseismic data, and from there we start our study. And the approach deals with training the model by using the real-time data from years, that which we consider from years, and then driving the optimization from this subspace. Otherwise, it is extremely difficult to deal with water flooding based problems. Acid gas sweetening, we are working a lot in this particular sector from last almost 1 decade. Still the work is going on, and the title is so wide that it will never end. That kind of opportunities we are able to see. Acid gas sweetening with retrofitting, acrylic acid production, carbon capture with sulfur recovery unit, methane pyrolysis for hydrogen production, waste tires for value-added fuel, steam methane reforming, and particularly its optimization, with steam reforming simultaneously with the carbon capture, etc. So out of so many problems that we have attempted and we have successfully solved, I will talk about in today's class lecture. I will try to talk about the biochemical process, where I will discuss lactic acid production process, oil and gas, where we'll talk about carbon capture process, and the green ammonia production process from the chemical sector. So the first title is cell recycle based continuous lactic acid production process. If I see the mathematical model or the schematic, we can see that there are two reactors here, reactor 1 and reactor 2, and the cells, in this case the viable cells, are recycled. They are separated and they are recycled back to the reactor. And this is how the industry is working in the real world. The cells are separated from the products and from the substrates and from the products, and they are recycled back. So the viability of cells has to be checked, whether the cells are dead or no, because we cannot deal with high temperature or high pressure in biochemical processes. So these cells are basically they are the live proteins. So to deal with live proteins in chemical processes is not that easy. The way we deal with a catalyst, though the dealing with catalyst is not that simple, but dealing with proteins or the cells is more difficult than dealing with catalyst. Number of equations have been used. And these are the four differential equations used for to model the two stage biochemical production process. So four different equations for first reactor, and similarly another four equations for the second reactor. We can see that number of variables are listed here, and we made an effort to collect the independent variables, and accordingly the equations are solved using Visual Basic, using the Excel in the macros formed by the VBA solver, using the VBA solver, and that have been linked with another Visual Basic code in Excel macros, and the data transfer has we have used Excel in this process. So Excel to the macros of optimizer and macros of solver. So they are interlinked together to get the results that we are going to discuss. In this case, the first job here was to tune the model. The very first task goes into tuning the model. So that tuning was done for different types of kinetic parameters. Kinetic parameters like the specific the kinetic constant for the specific growth, for the production, isn't it? For the dissociation, number of kinetic models are parameters. These kinetic models comes through the model itself, isn't it? If you see the model, these are present in the equations like Kp, isn't it? Like Kd naught, isn't it? So all those parameters are constants. So in the parameter estimation, we have targeted the variables which are kinetic in nature. Which are kinetic in nature. That means the one which are usually obtained using the experiments. Now, if you consider the efforts put in the past with the experimental approach to obtain those kinetic parameters, first of all, it is almost impossible, or it is very difficult to obtain the values of 9 or 10 kinetic constants through the experimental approach. Through experimental approach, we can deal with 1 or 2 or maximum 3 kind of kinetic constants in general. But to deal with 9, 10, 12 or more than 7, 8 number of variables is almost impossible. It becomes almost impossible, and it takes huge cost, huge efforts, and uncertainty range varies a lot when you talk about the experimental experiments and its range that we talk about within the budget available to the researchers. So finally tuned values are there, and then we can see that we got the objective function value. We got 0.03 compared to 0.26. So, and this is the prediction, model prediction we got for the substrate, for the cell mass. X is cell mass, S is substrate here, and P is the product. Product is lactic acid. The one which is getting decreased is substrates, and the two which are increasing are the one which is increasing exponentially and significantly are the products from the first reactor and from the second reactor, and similarly cell mass from the first and second reactor, and the substrates from the first and second reactor. How they vary with time, it's and that has been tuned through the optimization approach, and with the acceptable accuracy, we say. This work was published in Materials and Manufacturing Processes. Now, once the model was formulated, then we went into optimizing the process from the multi-objective perspective, and towards this, the productivity, substrate conversion, yield, simultaneously 3 different objectives have been optimized. So productivity was formulated from the equations itself. From the equations itself, we have formulated the productivity in terms of kg per hour flow rate. Conversion is formulated. So from the raw material, from the substrate, the idea here is that as we can see in the model, a lot of substrate in the experimental process, a lot of substrate was still present in the process, isn't it? Almost we can see that 2.5 kg per meter cube of substrate was, and the model was tuned from with the experimental data, isn't it? So we saw that there exists a good scope in reducing the substrate. There is no fun in keeping the substrate till the end of the time, because if it is present, then we also deal with separating that substrate from the product. So why don't we look for converting the substrate to zero range? And in this way, if you do that, you do not deal with zero substrate, but also that means zero raw material at the end of process. But also you end up with dealing with the cost of separation that usually is spent in the industry. Number of variables are used. What are those variables? These variables are the dilution rates, bleeding ratio, isn't it? And some of the constants in the equations, which have got direct impact on the model. SF1 and SF2 are the substrate feed rates to the reactors. Pressures of the reactor, because these are not very high pressure, so the constraint has been put on pressure on the conversions, and the range of S2 should not go beyond 0, because ultimately we are dealing with mathematical equations. So it is difficult to control the mathematical solutions. It may go into negative solutions, which may make our model unstable. So if you add constraints that if it goes to less than 0, then we terminate the process. We can multiply the chances of getting results with such kind of constraints. So constraints are thus not added from the process point of view, but they are also added considering the success rate that you can get in getting the results. Often many researchers, they deal with solving such kind of problems, and they end up with getting no results. So if they can focus on why they are not getting results, then issues can be resolved. So this particular process was solved on a very high-speed workstation with 128 GB RAM, and NSGA2 algorithm was used, which is a very popular algorithm proposed by Dev and their researchers. Professor Dev and his researchers. The lactic acid productivity and the substrate conversion, beautiful disconnected Pareto front can be seen. When I say beautiful disconnected Pareto front, that means it is first of all, it is extremely difficult to reach here, where our group have reached, and the disconnected Pareto front, it indicates that the process is highly unstable, is highly complex, highly nonlinear in the nature. So this non-linearity, this complexity leads to the getting the. Now we need to see why we are getting disconnected Pareto front, and that we discussed usually in the results. So we can divide from the understanding perspective. We can divide this Pareto front into three regimes, where 7 to 16 kg per meter cube productivity, 48 to 122 kg per meter cube, and third region is from 136 to 180, 170 kg per meter cube range. Now, if you see the variables, because what we got on the Pareto front is because of the changes in variables that we have which have affected the search space, isn't it? The objective space. So the dilution rate versus lactic acid productivity, and the dilution rate versus the substrate conversion. So if the dilution rate is low, the substrate conversion is high, but the productivity is low, isn't it? I mean, we are talking about the case where the substrate has got consumed, but no significant product has got formed. That means such kind of solutions are not going to be. So it says that in multi-objective optimization, to achieve the one objective, the second objective has to be sacrificed. So if you want to achieve the 100% substrate conversion, then productivity is sacrificed. And this is the reason also why we saw in the experimental domain, the substrate was kept unconverted, isn't it? Similarly, the bleed ratio 1 and bleed ratio 2 with respect to the objectives, we can say that they have got direct impact on the objectives. Other variables like feed glucose concentration and the flow ratio F1 F2 by F1 and flow ratio F2 by F1 for both the objectives also have got significant impact on the results, and which has been widely discussed in our article. The second case where yield and productivity are simultaneously maximized. Three objectives are simultaneously maximized for the same process, and as we say, more the number of objectives, more is the complex, and we can see the 3D solutions where the best optimal solution is also identified using the Pareto ranking methods, So now if you compare case 1, case 2 and case 3 of the results, we can see that when single objective optimization, two objective optimization, and when we change the approach from single objective to two objective to three objective, and three objective to further, then we can see that the single objective, when we solve from the single objective to optimization, we land up with the single solution. Against the single solution in multi-objective optimization, we can see we can get wide range of solutions, the one solution which are marked with blue range. For example, when the productivity is maximized, we got perhaps maximum productivity, but the range was not possible. In case of when the substrate was maximized, we got the conversion of 85%, but the diverse range was not possible. Similarly, in the second study, and its comparison with two objective and three objective optimization. Why the solutions are scattered in three objective optimization? Because we are dealing with three objectives simultaneously. So the solutions are scattered. The solutions which are shown are from the single objective optimization results. Results are compared with the The results are compared with the variables and why it is happening. We can see that the case with the single objective optimization resulted in maximum productivity, and that why the reason has been explored in the results in the analysis. If the maximum productivity is obtained in case 4, that is single objective optimization, why it has happened. So if you go into the variables, and if you compare the variables with the variables obtained where such high productivity was not obtained, like a very low productivity is obtained in case 1, isn't it? We can see why and how things are changing. Isn't it? Now, second and more complex and more interesting and more realistic problem from the industry is the carbon capture process. Now, before we go into the carbon capture, we should understand why do we capture carbon, from the natural gas. Because the CO2 that is present it becomes corrosive. It becomes corrosive, and it reduces it comes up with the problems of freezing of the gases and the erosion of the pipeline. So it becomes very important that we remove the elements like H2S and CO2 from the natural gas. And this purification process is called as gas sweetening process. So it's a traditional process. There is nothing like new in this process, where the amines are used to separate the CO2 and H2S from the natural gas, and we deal with huge amount of flows here. That means if in terms of standard meter cube, if I talk, it becomes almost 60,000-70,000 meter cube, which is very high. In kg per meter cube, it becomes almost more than 1 lakh kilogram per hour of flow rate. So with such a quantum of flow, and to remove the CO2 and H2S efficiently, it is very important that the process is run with optimum approach. In this process, in the traditional gas sweetening plant, we have added a retrofitted units. That means we have added the group of units, and we have called it as retrofitting using the rich vapor compression. So what we do, the rich amine which is coming from the absorber is separated into the gas and liquid through the flash, and the liquid part is fed to the top of the regenerator, and the gas is fed to the bottom of the so this way we found that it is possible to reduce the energy demand. Generally, the gas sweetening is considered as an energy intensive process. The energy demand is huge in gas sweetening processes, and that is also one of the big problem the oil and gas industries are facing, the large amount of energy demand. Dealing with generally gas processes are highly energy consuming processes. So this is the retrofitting unit, and what we did here is we built the model using the Promax software, and it involved the interlinking with Excel and with the optimizer, which is written in Visual Basic. So in this case also we made use of Excel's capability to solve such kind of problems, and these problems are that complex that it takes on an average 20 to 30 days to get the results that we are going to discuss today. The work that I'll be presenting here is already accepted in the Energy Journal here. I mean, recently the reviews are completed, and it is accepted in the Energy Journal. The model is validated with the acceptable accuracy, as you can see. In this case, the economic objective like cost of manufacturing, the global warming potential, and the second case we went for cost of manufacturing potential, and the 3 objective optimization focusing on economic, emission, and environment, and the safety objective like damage index, and dealing court case where all 4 objectives like economic aspects, environmental aspects, another environmental aspects of acidification potential, and the safety aspects together, considering the number of variables, number of independent variables, and keeping the constraints on H2S and CO2 levels in the sweet gas. The case 1 deals with GWP and global warming potential and the cost of manufacturing minimization. And the industrial data, if you see, we can see the industry is operating with the highest production cost. It is very difficult that that the industrial point also comes under within the same subspace, and it matches with our results, isn't it? That means where the industry is operating is also one of the because their focus is more into to reduce CO2. So, but as we know that CO2 can be it is permitted that CO2 can go up to 2%, 2 mole percent in the sweet gas. So there is no fun in reducing the CO2 to 0 value, and this is where the oil and gas are I mean, traditionally they are making this mistake. So this range of solution, where we say that we got equally good solutions, is possible, though the range is not that wide, but allowing the CO2 emission up to 2%, this range of solutions are possible. And the retrofitted solution, retrofitted design, indeed results in reducing the cost of manufacturing, though it involves fixed capital investment. So again, it's how the things are changing with feed gas pressure, with feed gas temperature, with recycle amine concentration, how the COM and the GWP are getting changed. Similarly, lean amine temperature, regenerative feed pressure, feed molar flow, feed molar flow. As you can see, very high molar flow, 1500 kilomole per hour, which is very high. And its impact on optimization is shown through the results here. The second case, a beautiful Pareto friend, where the normal operation and the retrofitted operations are shown. Different points are selected in this case, and they are compared among the normal operation and the retrofitted operation, and also with the industrial data. And it is shown through the in the tables which we are going to discuss. The third case is on 3 objective optimization, where the safety, like damage index based objective, cost of manufacturing, and the GWP are simultaneously minimized. Case 4, where 4 objective optimizations are simultaneously done, and they are shown here as 2 objective optimization. These results are published in recently. They are published recently in the Energy Journal. The comparison between 2 objective, 3 objective, and 4 objective optimization for a real world problem is shown, and we can see that beautiful disconnected Pareto friend solutions are. Imaginary Pareto friends can be seen. So this is the local Pareto friends, where we can, the way I am moving my cursor, isn't it? So these are the local solutions, isn't it? So though in 3 objective and 4 objective they are scattered solutions, but they ultimately end up with local Pareto friends. And because of the presence of the more number of conflicting solutions, they are compromised. Their solutions are compromised, or we can say their solutions are non-dominated compared to the 2 objective optimization results. For the selected solutions, for the normal operation and for the retrofitted operation. For the normal operation here, and similar results for the retrofitted operations are shown for the selected points. So we can see that an approach is followed here to discuss the result, which makes the publication in high impact, which makes the possible publication in the high impact. The study is extended further to see the process, environmental, and economic specific analysis, where from the process point of view, we considered the hydrocarbon recovery, H2S recovery, and economic perspective, we went for cost of manufacturing. So cost of manufacturing, economic perspective, hydrocarbon recovery is the process perspective, and the H2S removal is the environmental perspective. They are compared between the selected points, and we have discussed that the least value of hydrocarbon recovery or the highest value of H2S removal, it happens for 4 points, and that happens because of the lean amine temperature. Because the lean amine temperature has approached the lower bound, isn't it? So the single solution has got a big impact on the results, and we are dealing with thousands of gallons of oil per hour. So that shows the importance of solving such processes. Another viewpoint is looking into the sweet gas, H2S, and CO2 for the selected points, and in detail analysis has been reported in our study. I will be sharing our articles with the organizers, and they will be sharing the articles with you. Energy specific analysis is conducted, and again here A22 belongs to minimum energy requirement, and the minimum which also belongs to the minimum energy consumption, and the feed gas flow rate is and the amine concentration is said to be responsible for getting the minimum. We can see that feed gas flow rate and the energy values are amine values are reported here. For the normal operation and for the retrofitted operation. Process safety based analysis, where process safety objectives like toxicity and damage. Because we deal with H2S, so we formulated the toxicity based objective. Then we considered because we deal with high pressure process, so we consider the pressure and fire and explosion damage index, and the total damage index, which is the summation of those two. The thing that we can see here is that there is a distribution, isn't it? They are not neither they are all of them are high, neither they are all the selected solutions are low, and neither all the solutions are unique. There is a difference, isn't it? And this difference is considered as significant difference when we talk about the process operation. So that shows the importance of such study. That means getting the distributed solution. Even among the selected solutions, there is a distribution. Life cycle based analysis is again conducted and shown here. Life cycle based objectives here are global warming potential, human toxicity, and photochemical ozone creation potential. POCP we call. So detailed analysis. We made use of 10 different Pareto ranking methods here, like 10 different methods like CODAS, COPRAS, Electra 1, Electra 3, Electra 2, Electra 3, HUCA, GRA, LinMap, MABAC, MU, and NFM. 10 different methods for the normal operation, and for the again 10 different methods for the retrofitted operation. These solutions are ranked, and they are for each case, for the normal operation and for the retrofitted operation, are compared and shown using the NFM, using one of the method. One out of those 10 methods is used to rank and show the top 5%, top 10%, and top 15%. So these solutions are what are those objectives? Those objectives are related to the sustainability. Those objectives are related to when we talk about minimizing the CO2 emissions, minimizing the energy, we talk about green processes. When we talk about enhancing the cost, minimizing the cost, enhancing the productivity, by utilizing the resources, that talks about the sustainability. And when you talk about dealing with the production and the emissions together and safety together, we treat it as sustainable and green approach. Between the normal operation and the retrofitted operation, we can see that there is a significant decrease in the changes in the cost. In the cost of manufacturing, 17 and 16.2 million US dollar per year, and there is a significant changes in the AP values, acidification potential values, almost 3365 MPET European Union 2004 and the 634 AP values. So significant changes are present. That shows the impact of retrofitted based optimizers. The third process, I think I'm in time. We'll finish by 7:15. The third process is on green ammonia, large-scale green ammonia production using the water electrolysis-based green hydrogen. The ammonia, as we know, it is considered as one of the important products, just not from the as a cryogenic fluid, but also as one of the chemicals where the hydrogen can be stored. It is possible that now it is ammonia is considered as a product where ammonia, because ammonia is low in a specific volume compared to hydrogen, so it is easy to store ammonia and then convert hydrogen from the ammonia. The ammonia production rates are shown here, but considering the increase in hydrogen demand, this production is going, this statistics is going to increase significantly. Among the different regions, the maximum comes from the East Asia, which includes China, India, and North America, almost 12%, Latin America 4%, and Europe 12%, isn't it? And so major is from Asia and America, the ammonia production. Now there will be a growing demand, as we said just now. While meeting the demand, attention should be given in lowering the energy consumption and reducing the emissions. Currently, ammonia production consumes around 2% of total final energy and contributes 1.3 of CO2 emissions from the energy system. It's a huge contribution, we can say. 2% from the final energy, and so we can say that it's a significant energy that is involved in the production of ammonia. So if we can focus the objective like energy, we are directly contributing towards the sustainable and green approaches. The biggest contributor to energy consumption of ammonia industry is natural gas, is 70%, followed by coal and electricity 3%, and oil 1%. As we said, we made use of water electrolysis process. So the first section here, it shows the polymer electrolyte membrane electrolyzer PEM model, where we made use of electrolyzers to convert water into hydrogen using the current density and using the current and that approach. And then once the hydrogen is produced, then hydrogen is hydrogen along with the air is used to, along with nitrogen, is used to get the NH3 in three reactors, in three connected reactors. In this case, we maximize the production rate, we minimize the production cost, and we may minimize the total energy. and it is subjected to number of more than 7 or 8 variables. That means when I say 7 or 8 variables, that means we are talking about multi-dimensional subspace. Just to show you here, when I say two objective optimization, I deal with x1 and x2 variables, isn't it? I deal with x1 and x2 variables. So one point here will give me one x1 value and one x2 value, isn't it? But when I bring another variable here, like this is temperature, x1 is temperature, and pressure is x2, temperature and pressure, two objectives, that means two-dimensional subspace. But when I bring third variable, temperature, pressure, and the concentration. So one point on the subspace will give me what? One value of temperature, one value of pressure, and one value of concentration and the pressure. When I bring the four-dimensional subspace, so one point in the subspace will give me one, then second, and then third, isn't it? Because this will be this is the operating point, isn't it, in a given subspace. So one point will have that many axes. Now when I say 8 or 10 dimensional subspace, so you can imagine the complexity that we are adding to the optimizers. The solutions are not that straightforward. They are not as simple as we see in a two-dimensional subspace, where we can make a challenge, we can make a daring to solve even by hands, isn't it? Two-dimensional subspace problems can be easily solved using the traditional methods, or using the even sometimes with extended efforts with hand calculation. But dealing with 3, 4, 5, 6, 7, 8, or even more dimensional subspace for such a complex process, such a complex industrial process, and where we are targeting the objectives like environment, energy, emissions simultaneously, the solutions are indeed not straightforward, and that makes the publication possible, in the high impact journals. So in this case, also again, bi-objective and tri-objective cases are constructed, consisting of the process and the cost economic, isn't it, and the energy, isn't it? So process base means production rate, and cost is economic. So here is the process and energy, and here is all three of them together. The production rate, the economic aspects, and the energy aspects simultaneously are optimized. In this case, the work was published in International Journal of Hydrogen Energy recently. The green hydrogen and ammonia. Green hydrogen because we get the hydrogen using the water electrolysis process. The ammonia is produced and then it is optimized simultaneously using the multiple criteria. Those criteria included ammonia production rate, total production cost, energy. We made use of Pareto ranking. We made use of MOOPS spatial solutions, and we made use of the global warming potential, and CO2 emissions, energy, and heat credits based analysis. So statistical analysis of different factors is conducted. A beautiful plot where the broken axis is shown here. Isn't it? The broken axis is shown here from 10 to 35, isn't it? Because the range is that wide. Because the base case results are far different than the optimum results, isn't it? The base case results are far different, and they lie far away from the. So accordingly, the axis is broken here. Axis is broken and shown. Solutions are shown. Where we deal with 11.2 2 kilomole per hour, and where we deal with 66 kilomole per hour. So that's the difference that we can see between the base case and the optimum solution. Again, the results shows here that different decision variables have shown an impact on the objectives. Reactor 1 temperature varies from 624 to 697, but whereas reactor 2 goes to a relatively high temperature. Why it goes to the higher temperature? Because ammonia, if you look into the Haber-Bosch reaction for the ammonia production, it's a reversible endothermic reaction. So higher temperature and the lower pressures are favored for such reversible endothermic reaction, as per the Le-Chatelain's principle. So when we say that optimization of a given process, it is just not optimization of given process. It is the optimization of given processes, considering the reaction kinetics, considering the rules that are followed in the reaction kinetics, considering the thermodynamic aspects, considering the ranges and the methods that the particular thermodynamic methods are following, and indeed the numerical approach, the ability of numerical solutions, or the solvers, to give the solution, to solve the model, and to end up with solutions, not with the errors, not with the inaccuracy, not with the unstable solution, but the feasible solution. Their ability, all those aspects, the ability of solutions, the nature of the process which involves the reaction kinetics, their rules, their as we know, the single reactions are different than multiple reactions. Reversibility is another aspect, isn't it? The endothermic reaction, the exothermic reaction, simultaneous reactions happening together. So the thermodynamic aspects, isn't it? So all those aspects as a bundle, if you consider the process optimization as a bundle, it leads to a highly complex domain. And by considering the objectives like total energy and the production, we are taking this title towards to sustainable and green chemical technology. That means in this talk, I have selected that product, which is considered as a storage carrier for hydrogen in the coming time, and where the sustainable approaches like the energy and the production rate are simultaneously targeted. The three objectives together towards the sustainability. I can show you this. I don't know whether I can get the. I can see the article. I can show you this article. The title itself is sustainable. So if you see the title here, it's in the title itself we are able to bring the process development and sustainable, and green, isn't it? So the talk that I'm giving is highly specific to green and sustainable technology. And what I'm presenting here is all reported in the what I'm discussing in the slides here, isn't it? The process model which I have shown in 2 sections, and the beautiful chart which I have already discussed with you, isn't it? And the figures which I'm going to discuss here now with you, isn't it? And the major impact that I'm going to show here is on how the solutions are obtained. The time is too small. No, we cannot go to that depth. But as I told, I'll be sharing my articles, these articles with the organizers. We can share with you. They are quite interesting to read. The special solutions are identified. Special solutions like Nadir solution, like Z Nadir, utopian solutions, Z utopian, Z Nadir, Z ideal, ideal solution, utopal solution, nadir solution. Typically, such kind of mathematical analysis is rarely done for chemical processes. And for this real world process, we were able to report the mathematical aspects like nadir solution, utopian solutions, ideal solutions, and that has been published in the International Journal of Hydrogen Energy. The Pareto ranking is again applied here, and the top 5 rank solutions are shown for different cases: case 1, case 2, and case 3. Ranking from the Pareto ranks, top 5 rank solution from the ranking sorting that we got, and it's detailed impact from the indirectly varied variables on the given objectives of productivity, cost, and the energy has been shown here and is compared. It is compared statistically, where median, mean, and the 25 to 30, this shows the 25 to 75% of the range. This shows the minimum and this shows the maximum. For different cases is shown, and these are the cluster of solutions in the through the statistical analysis perspective. This is for another case of energy and environmental specific optimization, where the heat credits, global warming potential, are shown here. In the previous case, the energy consumption and the CO2 emission was shown, isn't it? So the energy and energy specific statistical analysis is shown for the best optimum solutions, the one which you got in different cases: case 1, case 2, and case 3. And its contribution is also further extended, that which are the equipments responsible for consuming the energy. So we can notice here the PM electrolyzers are the one which are consuming higher energy even compared to the compressors. So contribution we can see. And perhaps last slide here, but very, very deep from the understanding perspective. We are talking about this process where we are considering the energy, in different cases here. So the energy, as we can see here, the energy which was quite high, we are able to convert that negative energy into the positive energy. Between the heaters and coolers, the energy which was getting consumed, we were able to convert that energy into the energy produced. So this kind of realistic results are possible when you consider number of variables and give the freedom to the process, which is typically not done with the industry. In the industry, the engineers' hands are quite tied. They are unable to make decisions. They are unable to take decisions to further level. So through this process, an approach has been shown that the negative energy can be converted into the positive. The energy consumed can be converted into the energy emitted, isn't it? That's the sustainable and green chemical technology applied on ammonia production, isn't it? I will just conclude my presentation. I think we are on time. The process industries are under tremendous pressure to meet the market demand with the product quality. This leads to challenges not only on economic front, but also in sustainable environment, safety, and energy criteria. These issues show challenges that need to be addressed for highly complex and non-linear chemical processes. Evolutionary multi-objective optimization approaches sheds light on such criteria, which can be adopted successfully by the industry towards a greener and cleaner tomorrow. for the sustainable green chemical technology. Thank you.
Thank you, Ashish sir. Your presentation shows that what kind of a deep research you had been carrying on and doing such kind of a deep work. Thanks for the presentation. The kind of tools you have been using, that VBA tools for the converting the these particular techniques and all the things. So I think all creditable. I think the forum is open to all. Ingo sir, can you unmute the participants so that if there are any questions, so that we can just go through the question and answer session?
Open, sir.
Okay. So participants, any question?
One question
Yes,
is from Saurabh Zoglekar.
Can I
Sir,
read it?
good evening. I'm Dr. Saurabh Zoglekar from LIT University, Nagpur. Sir, I was just curious. I have been working in the sustainability domain, primarily into evaluating the environmental impacts of processes. And I have had worked on not this deep, but I intend to work in this domain. Sir, can you please guide me in understanding what a typical infrastructure requirement for working around all these optimization tools, so that I can start preparing for it, and then maybe I can work in this domain.
you see, the infrastructure, our hands should not, we should not tie ourselves towards what are the limitations. No, we should look for what is available with us, isn't it? So the tools that we require here is the software, which can be either tools like Promax, Aspen Plus, Aspen HYSYS, or ChemCAD, or any other pre licenses that we have. And it needs an optimizer where we can write a code, and the code has got an ability to interact with the softwares, isn't it? So we need Excel, we need MATLAB, we need Python, So to me, if you ask, it depends on the problem. The resources that we need, it depends on the problem. If you select the problem, for example, hydrocracking. So hydrocracking process, if you attempt to solve using first principles modeling, it will take years for us to model. PhDs are done at IIT Kanpur under the Professor Gupta's leadership. Professor S.K. Gupta's leadership. That kind of effort will take long time, PhD, 4-5 years, and a lot of uncertainty there. Instead of this, what we can do, we can make use of Aspen HYSYS. We can get some industry data, and we can tune the available models in Aspen HYSYS, and then that we can link with MATLAB or Python or so. If we know how to link the resources, we can see that there is a success. But often different obstacles are there. They are not that straightforward. So your answer, I will give in one line, that typical infrastructure depends on the problem that you are dealing with, and then tune ourselves to that kind of resources. You make yourself able to get extra knowledge. Like, we were not knowing Visual Basic, we were not knowing Python, so we were not knowing the coding in Visual Basic or in Python at one time. So we made an effort to learn it, and then progress further, and we see that we were able to do it, because when I started my research, I was not knowing all those languages. I was mostly but knowing that I'm good in programming, I can always learn new languages and new platforms, new softwares, and that makes our resources possible to impact. You can email me, Dr. Jogrekar. You can please email me if you want to,
Absolutely,
if you need
sir.
any help,
Absolutely,
or
absolutely.
if you want to collaborate. Thank you.
Right, sir. Sure. Thank you so much.
What is the NFM? Another question. NFM is net flow method. It's a Pareto ranking method. As we said, there are a number of methods to rank the solutions. Now, Dr. Brushali, as we said, we come up with multiple equally good solutions in multi-objective optimization. So now how the decision maker will select which solution is good. So to come up with the ranking, that solution 1 is this, solution 2 is this, as per the ranking method, no? So which can help the decision maker to select the solution, as per the ranking. So for that, the different methods are used, and then one of the method is NFM, which is net flow method, which is the net flow method. No, sorry, it's a net flow method.
Okay, any more questions?
Hello.
Yes.
Hello. Good evening, sir.
Yes. Yes.
Sir, you mentioned that in the two-stage fermenter, the separation of cells will take place, right?
Yes.
And it is recycled.
Yes.
So how many times that can be recycled to reduce the process cost to, as we can say?
We have studied that aspect in our case. It depends on, I mean, obviously, we cannot go for infinitely using those cells. So there would be a dead cells, and these dead cells are separated basically in the so
As
we
like a
know the
debris.
amount of
You can.
debris, and because they are live materials, the one which will be die, and the cells which are proteins, which will not viable, which are not viable. So they will be, so the amount which is removed, that much equal amount is easily added. So if you see in the model, we have fresh, cells are also coming, in the process. That value is equal actually.
Means
to
what
what is being lost.
concentration of the new cells using and recycled concentration? Means what is the proportion of that?
As we say, the cells are considered as active, isn't it? So
That means we are analyzing the activity of the cells after the separation, right? After washing and no.
yes, after separating.
Okay. And in your case, whether these cells are working on the extracellular or intracellular? Suppose most
are
of the
working on
time the cells are used. Yes.
Go ahead.
Means biotechnology processes use such type of the cells to produce
Yes.
the valuable compound, right? So
Yes.
means whether it is in your case, it is a extra or intracellular cells are used. Means
Here, ma'am,
working of the
as far as I remember, we made it of intracellular, but because we dealt with tuning the model with someone's experimental data, so their efforts in dealing with the quality of cells, their efforts in dealing with the intracellular, extracellular, the size of the cell, those aspects, that depth we cannot bring here in our study. But indeed, when I say that model is validated, so that becomes the starting point for our study, and we come up with accurate validation, and so those aspects of the typical biochemical engineering. To me, what we do, what we can achieve from here, so that the starting point we consider as model validation. So indeed, each study has got a lot of drawback. What biochemical engineers cannot do, we are able to do. What we do, we cannot do. We don't have lab facilities. We don't have that kind of knowledge, which the biochemist and the biochemical engineers can contribute towards towards getting the extra knowledge about the cell mass and its variation. In our case, is dealing the problem. Each problem for us is a mathematical problem. That makes our study. We see that yes, it is possible. Then we look into non-linearity aspects, which is impossible for the biochemical engineers to study. So to your question again, ma'am, it's the intracellular yes, please go ahead.
Means the difference between the intra and extracellular. Yes.
Yes, it's the intracellular from the literature that we have studied. but it has not been considered in our model. Our model is as a non-linear multimodal kind of app, which is successfully validated with with someone's experimental data. So the intracellularity or extracellularity aspect has not been explicitly considered in our model.
Okay, okay. Okay, sir. Thank you.
Are there chances of cell death rate KD? How you consider during? Yes, we considered the in polymers we do consider. No, there are different methods to deal with the they are not straightforwardly calculated, but they are calculated using the method of moments. The first order moment, second order moment, third order moment, higher order moments. That they can give us the idea about the live mass and the dead mass. So method of moments is quite popular. That means we convert the equations into the in the moment form. And Fogler, 13th chapter on RTD, it gives the definition about it is giving the definition of method of moments. Those moments, if you bring the first moment talks about the residence time distribution. Second moment talks about the spread of the solution, and the third moment talks about the distribution. If you extend the definition of moments towards the dead and live, you will find multiple articles, where people are able to convert able to measure the cell density in terms of their deadness or the liveness. So in LDP, in PTA, in PET, in nylon 6, in styrene, we made use of method of moments to quantify the live and dead cells.
I think
Any question?
any more question? I think Ashish sir, that at the time when we had been learning the engineering, we was not been familiar with all these particular new technique, tools, and whatever the software. But at that time being, for our sustainability, we had been started learning all these particular things. Even I know that when we have been starting, we were not having this particular software. We had been hands-on this software and all the things. But nowadays, we all, for the betterment of our chemical engineering, we had been familiar with all these particular software, and it's a good thing that some particular young researchers and young academicians have been coming forward, and we are doing all this particular thing in a well manner. So thank you so much for this all wonderful presentation, sir. So
highly appreciated.
Yeah.
Adding to your value for all our young research students, always remember that we are dealing with a world where the new knowledge can be added. We can acquire new knowledge, but remember, acquiring the skill is not important. It is a very well-known proverb said, "Jungle mein mor nacha, kisi ne na dekha." That means in a forest, the peacock has danced beautifully, and there was very good environment. It was raining, isn't it? But nobody has seen it. So this is what we do when we say we acquire skill, isn't it? You acquire skill, you become expert. But if you don't show it, if you don't apply it, then you become the similar peacock, which has danced a lot, which has acquired a lot, isn't it? So apart from acquiring, you get in touch with the professors, you get in touch with the doctors in your domain, or the world has become very small these days, isn't it? You get in touch if your area is different than which you don't have there in your college. You expand further. You expand to different websites and acquire those knowledge, and then try to apply and try to publish or come up with conferences or link it with the industry results. Publish it so that it becomes acquisition and the application of newly learned knowledge, and this is how we learn.
Absolutely true. Absolutely true. So we conclude today's session.
Sir, just one request in. Ashish,
Yes,
sir, will you share your PPT for the model with us?
Yeah, PPT, yes, surely PPT and our research articles.
Yeah. Thank you, sir.
They will research articles also I'll share. So I will share with the organizers, and they will be shared with all of you.
Okay, sir. Thank you. Thank you.
So
Thank you.
we'll conclude today's session. Dr. Ravi Tapre, will you
Yes,
just
sir.
formally we will be concluding the today's session by formally giving the vote of thanks for today's session.
Yes, sir. On behalf of the Atal Faculty Development Program team and all participants, I would like to extend our heartfelt gratitude to Dr. ASHISH GUJRATHI sir for delivering such a remarkable and intellectually stimulating session on sustainable green chemical technology. Sir, your presentation beautifully bridged the gap between the academic theory and industrial application, helping us understand how innovation and sustainability can go hand in hand. Your articulation of green process optimization strategies and future-ready technologies have opened our mind to new dimensions of research and practical implementation. What made today's session truly special was not just the knowledge you shared, but the clarity, passion, and the vision with which you inspired us. You have encouraged us to think beyond conventional practices and embrace sustainability not as an option, but as a responsibility. Once again, thank you so much, sir, for gracing us with your presence and wisdom. We truly look forward to more such opportunities to learn from you in the future. With deep respect and gratitude, thank you, sir.
Thank you, Ashish sir, so much.
Thank you, Satyaji sir, and thank you, Ravi. Thank you all.
सेशन लिंक आई भी है
Once, once again, wish you a many happy returns of the day, sir.
Thank you very much.
You might be having some birthday plannings, and we had been asked you to have the presentation today.
Today is Karwa Chauth, so no birthday, no party. So I will be going home now.
Okay, sir. So thank you so much.